Let's do some problems on applications of Sylow's theorem. Of all three Sylow's theorems, applications of the Sylow theorems. Okay, so here's the first problem. Suppose G is a finite group whose cardinality is 12. Okay, then prove that. So maybe we should give it Sylow's subgroup a name as well. So let H denote a Sylow 3 Sylow subgroup of G. So 12 of course is 3 into 4, so that's 3 into 2 square, that's the prime factorization. And so by Sylow's theorem we know that there is a 3 Sylow subgroup, which is basically a subgroup whose cardinality is 3 power 1. So pick any such subgroup and call it H. So then what we need to prove is the following. Then prove the following: either H is normal, in G, so it's a normal subgroup, or the group G is isomorphic to A4. Okay, so this is what we need to prove. Either the 3 Sylow subgroup is normal in this group, or the group itself is isomorphic to the group A4. Okay, so let's work out the solution to this problem. First, let's recall what the group A4 was. So what's A4? This is what we call the alternating group. So you encountered this once before, the alternating group on 4 letters. How was it defined? So if you look back on the lecture on normal subgroups, you will recall that this was defined as follows. So in general I take Sn, or in this case, let's do it for this case, I take the symmetric group S4 of all permutations, and I can actually map this to the group of all, so let's call it GL4, C maybe, complex 4 cross 4 complex matrices which are invertible. And how do I do it? I take each permutation sigma in S4 and map it to the corresponding permutation matrix. So recall we have what's called the permutation matrix associated to each permutation. And how do you get it? Well, you start with the identity matrix, right? So I have the identity matrix whose columns are 1 0 0 0 0 1 0 0 etc. So that's my identity, and then the permutation matrix of sigma does the following: it takes the columns of this identity matrix and permutes these columns according to the permutation sigma. Okay, so I sort of have to just permute my columns according to what sigma does. Okay, so this is just something for you to recall if you look back on the lecture on normal subgroups. So this is a homomorphism of groups, mapping a permutation to the corresponding permutation matrix, and I can further look at the determinant map. So I can further compute the determinant of each permutation matrix. It turns out it's either +1 or -1 in general. So the determinant actually maps to, so the determinant is a map which takes an invertible matrix to a non-zero complex number, so which I will denote as C with a cross on top. So this is the set of all non-zero, the multiplicative group of non-zero complex numbers. And the so if you sort of take this composition of these two maps, to each sigma you associate the determinant of its permutation matrix, and so you get a homomorphism and the kernel of that entire homomorphism. So kernel, so how did we define the alternating group? Here's one way of defining it, is nothing but the kernel of the homomorphism from S4 to the multiplicative group of complex numbers, where this homomorphism is defined by saying each sigma maps to the determinant of the permutation matrix of sigma. Okay, so this was how it was defined. So kernel of, so in this case the multiplicative group of complex numbers, non-zero complex numbers, it has identity being the number 1. So what we are saying is it's all permutation matrices whose determinant is +1. Okay. So of course this is one way of defining it. Another way of defining it is to say somewhat more concrete, easier to understand. We say that this alternating group is nothing but the set of what are called even permutations of 1, 2, 3, 4. So what is the set of even permutations? So recall that any permutation sigma, so if sigma is an element of S4, any permutation can always be written as a product of transpositions. Okay, so what's a transposition? A transposition is just a permutation of the form ij, which means that it leaves all the other numbers fixed and it sends I to j and j to I. Okay, so that's a transposition. So this sort of permutation is what we call a transposition, and it's a fact that any permutation can be written as a product of transpositions. Okay, this in general. We say that a permutation is even if it can be written as a product of an even number of transpositions. Okay, so we say that, so this is the definition, sigma is said to be an even, is an even permutation if sigma can be written as a product of an even number of transpositions. Okay, and turns out that this is another way of saying the same thing. The determinant is +1 is the same as saying that sigma can be written as a product of an even number of transpositions. Okay, and the other important fact about A4 is that the cardinality of A4 is exactly half the cardinality of the entire symmetric group S4. So S4 is 4 factorial cardinality, which is 24, and so this is 24 by 2, which is exactly 12. Okay, now let's look at what we need to prove. We are given the 3 Sylow subgroup is called H, and so we know, let H be what's given. This was the 3 Sylow subgroup, and since the cardinality of G was 3 power 1 into 2 power 2, the cardinality of H will just be 3 power 1, the maximum power of 3 which divides the cardinality of G. Okay, now what we need to prove, let's look back on what we need to prove. Either H is normal or G is A4. Okay, so let's do it as follows. Let's assume that H is not normal. Suppose H is not normal. Okay, we will show, we need to prove that the group then is isomorphic to A4. Okay, so this is our goal. Let's try and use the Sylow theorems. So we'll use, for a start, let's look at the third Sylow theorem. So we'll first apply Sylow theorem number 3. what does this say? It talks about the number of 3 Sylow subgroups. So let M denote the number of 3 Sylow subgroups. What the third Sylow theorem says is that this number is congruent to 1 modulo 3. Okay, what that means is that it can take one of the following values. It can be 1, 4, 7, 10, etc. Right? It's one of these possible numbers congruent to 1 modulo 3. Okay, now let's try and understand this 3 Sylow subgroup a little better. So suppose if I have two 3 Sylow subgroups, so I have H prime, if H prime and H double prime are both 3 Sylow subgroups, are two distinct 3 Sylow subgroups, then what does that mean? Let's try and draw a picture. So I have H prime. What does it have? It's got an element E. Let's call the other two elements as A and A square. It's a group of order 3. It's got to be cyclic. Now I take H double prime, which is another such guy. Now the point is that these two subgroups, if they are distinct, then this automatically means that their intersection has to only be the identity. So I can only get H double prime looking like this. There should be another B and a B square. Okay, why is this? Because, well, their intersection is after all another subgroup, right? The intersection of two subgroups is a subgroup, and this is a subgroup of both H prime and H double prime, if you wish, and it's got to be a proper subgroup because H prime and H double prime are two distinct sets, or they are not equal to each other. So this intersection has to be a proper subgroup of H prime. Okay, but H prime has cardinality 3, and so if you have a proper subgroup, then that's only got to be cardinality 1. Okay, so this tells us that any two of these 3 Sylow subgroups, they must intersect in this manner. They have to have the identity common, but the other two elements are separate, meaning they have no intersections. Okay, so what does that tell us in particular? So if you look at what each 3 Sylow subgroup therefore contributes, there is the identity, and then there are two elements of order 3. So observe this A square, B square, and so on, they are all elements of order 3, right, because the group has order 3. Okay, so what does a subgroup, a 3 Sylow subgroup contribute? There is one identity and two elements of order 3. These are both elements of order 3. Similarly, if I take the other 3 Sylow subgroup here, it's got these two elements whose order is 3, okay, and so on. So in general, I claim a little observation here is that the number of elements of order 3, the number of elements of G of order 3 is exactly 2 times the number of 3 Sylow subgroups M. Okay, I claim that this must be true. Okay, so a moment's thought should convince you that this is in fact right. Why is this? Because if on the one hand, we have just said that if I take a 3 Sylow subgroup, it contributes 2 elements of order 3. Okay, and these elements are all distinct. If I take two different 3 Sylow subgroups sort of intersecting each other, I get 2 elements of order 3 from one guy, 2 other elements of order 3 from the other subgroup. So it's clear that there are at least these many elements of order 3 in my group. Okay, but if on the other hand, if I have an element of order 3, then it generates a cyclic group of order 3, okay, which is automatically a 3 Sylow subgroup. Okay, so any element of order 3 necessarily belongs to some 3 Sylow subgroup. Okay, so I sort of orally described the argument, but I'd like you to try and formulate this into a rigorous sequence of steps. So proof exercise. Okay, So now we sort of understand what these 3 Sylow subgroups are good for. They contribute elements of order 3, they contribute 2 elements of order 3 each. And so now we already said what are the possible values of m. They can be 1, 4, 7, 10 and so on, but we can already see that 7, 10 and so on are all not possible values. So I cannot have m equals 7, because if m is 7, that will tell me that there must be 14 elements of order 3 in my group, but my group itself is only of order 12. Okay, so all these numbers 7 and higher will turn out to be not possible. They cannot be values of m, because they will tell us that there are too many elements of order 3 in my group. Okay, so observe that m has to be 1 or 4, since the group itself, so since 2m, the total number of elements of order 3, can at most be the cardinality of the group. Okay, and the cardinality of the group is 12. So this tells us that m is at most 6, for example, and among the possible values 1 and 4 are the only ones which satisfy this inequality. Okay, so there are two possibilities, m is either 1 or 4, and let's see which of these is indeed possible. If m is actually 1, what does this mean? This means that there exists only one 3 Sylow subgroup. So there exists a unique 3 Sylow subgroup. Okay, but what does this mean? So recall all 3 Sylow subgroups are mutually conjugate, if you wish. That's the second Sylow theorem. So in this case, so H, so this H is the unique. We already gave it a name. We picked one of them and called it H. H is the unique 3 Sylow subgroup. Now what does that mean? If I conjugate H by any element of the group, that's again a 3 Sylow subgroup, because its cardinality is 3, but there is only one 3 Sylow subgroup, which is H itself. So this must be true. The conjugate, any conjugate of H must coincide with H. Okay, because any conjugate of H is also a 3 Sylow subgroup. This is also 3 Sylow. Okay, now what does that imply? That tells you that H is normal. Okay, every conjugate coincides with the group itself, the subgroup itself. Okay, but we had assumed to start with that H is not normal. That was our hypothesis. Okay, so that implies that therefore m can't be 1. So this case cannot arise. So we conclude therefore that m must be 4. So the final conclusion here is that there are exactly 4 3 Sylow subgroups in my group G. Okay, so let's see what that will give us. So let's try and draw the same sort of picture that we drew before on how many elements there are of each of order 3. So let me draw my 4 3 Sylow subgroups like this. So here's my 3 Sylow subgroup. Identity a square, maybe identity, and then 2 more elements b square. So this is my identity element. So here's a third of the subgroups, identity c square. So I'm just drawing my 3 Sylow subgroups, c square, identity d square. Okay, so these are all my 3 Sylow subgroups. I have 4 of them, and this accounts for 8 plus 1 9 elements of my group. So I know there are 3 more elements left. So what does my group look like? There are 3 more elements left in my group. So what I have drawn here is a picture of my group G itself. Okay, so think of this as my group G now. Sort of have some understanding about the orders of the various elements, for example. Okay, so of course I am saying a cubed, b cubed, c cubed and d cubed are all equal to the identity. So maybe let's call that 1 instead of e. So they're all equal to 1. Okay, now what is it that we now need to prove? We need to show that the group G is isomorphic to A4, right? That was our objective. Now why should this group be isomorphic to A4? In general, when you're trying to prove statements like this, that a group is isomorphic to say maybe some symmetric group even, or a group is isomorphic to some subgroup of a symmetric group, the way one tries to establish facts like that is by constructing an action of this group G on a set whose cardinality is 4, for example. So in our example, so what we want to prove, we want to prove that G is isomorphic to A4. A4, remember, is some subgroup of the symmetric group S4. When you want to do a thing like this, we will do it as follows. We construct an action. We will construct an action of the group G on a set X with 4 elements. Okay. Now, why does that help us? Why should we try and do it in this manner? How does that help? Because recall from the earlier set of problems that we did, group actions can be thought of in an alternative way. If a group G acts on a set X, so recall, when I have this means I obtain a group homomorphism from the group G to the group of all permutations of X, okay, or all bijections from X to X. And if you recall, how was this map defined? Each group element G was mapped to a certain permutation called phi sub G, where phi sub G was defined as follows. Phi sub G is a permutation of X, which is just G, phi G of X is G acting on X for all X and X. Okay. So this is a group homomorphism. So phi is a group homomorphism. Recall, given a group action, there exists a group homomorphism. Okay. So if I construct a group, an action on a set of 4 elements, then what I will get at least is a homomorphism from my group G to the set of all permutations of a set of 4 elements. Okay. And permutations of a set of 4 elements is like S4, right? So it's the symmetric group. So at least we will get a map, a homomorphism from G to S4, and we will then try and prove that this homomorphism is 1-to-1 and its image is exactly A4. Okay, that's the idea. That's going to be the strategy. Okay. Now, how do we construct this set X? So, in this case, firstly, let's look for a set of 4 elements. It turns out the correct object to take, I mean, there are many possibilities, but the correct object to take is what I have denoted in this diagram here, is the set of these 4 subgroups. Okay, there are 3 Sylow subgroups, and this 4 element set, which comprises these 4 subgroups, is what I need to take. Okay. So let's make that precise. So let's take X. So I'm going to define X. Define X as follows: be the set of 3 Sylow subgroups. Of G. So I know there are exactly 4 of them. Okay. Now let's construct an action of G on X. Okay, that's easy too. It's sort of natural. We just take the conjugation action. So what do we mean by that? We just take G acting on any one of the Sylow subgroups will just give me G H prime G inverse, the conjugate of that guy. Okay, and what Sylow theorem 2 tells us, Sylow 2 tells us that all the Sylow subgroups are mutually conjugate to each other, right? So what Sylow 2 tells us is that this action is transitive. In other words, that there is a unique orbit. Okay, Sylow 2 says that there exists a single orbit in this case. or to use a word which we introduced in the earlier problem session, i.e. This action is transitive. This action is transitive. Okay, so the conjugation action on the set of 3 Sylow subgroups is transitive according to the second Sylow theorem, and that's a set of 4 elements. Now let's see if that gives us what we want. So now by our earlier principle, by the general principle I just talked about, which implies I get a group homomorphism, let's call it phi, from G to the set of all permutations of X. Okay, and the permutations of X, as I just said, is like the symmetric group S4, because X has exactly 4 elements. Now let's try and establish the following facts. Claim phi is an injective map. In other words, it's 1 to 1, and the image of phi is exactly A4. Okay, is isomorphic to the subgroup A4 of S4. Okay, so let's see how we would establish these 2 facts. So proof of claim. Recall from the problem that we did last time, in the earlier problem session, that we actually know how to compute the kernel of this homomorphism phi. Okay, so the kernel of this homomorphism, when you have a group action and you consider the corresponding homomorphism, the kernel of that homomorphism, we said, is nothing but the intersection of all the stabilizers. Okay, so I have to compute the stabilizer of all the various elements of X in this case. Now what is that? So this is just the intersection of the stabilizer of H prime. Let's say H prime is any one of the 4 3 Sylow subgroups. Okay, and what does stabilizer now mean? Stabilizer by definition for the conjugation action, where when I say this stabilizer, so I am just using this notation stab for stabilizer. Stabilizer of H prime by definition is all those group elements which act on H prime and leave it fixed. Okay, so G H prime G inverse is should equal H prime, and this is what we usually call the normalizer. So this has another name. This is sometimes called the normalizer of the subgroup H prime. Okay, in general, the normalizer of a subgroup is nothing but the stabilizer of that subgroup under the conjugation action. Okay, so we are talking about the normalizers in this case. Okay, now let's see what else can we conclude about the stabilizers. So recall from the orbit, the counting theorem, not the one which counts orbits, but the cardinality of an orbit. So recall how does one find the orbit of H prime, the orbit stabilizer theorem. So the orbit is related to the stabilizer in this way, right? That's how we find the stabilizers. At least the cardinalities, if you know the cardinality of the orbit, that determines the cardinality of the stabilizer. Now observe, in this case we know the cardinality of the orbit, right? The orbit, as we just said, it's a transitive action. So all 4 Sylow subgroups are in the same orbit. So if I start with any H prime and I apply the conjugation action, I get all the other 3 Sylow subgroups. So the orbit is equal to the entire set X. Cardinality is 4 and cardinality G is 12. So from this I conclude that the stabilizer of H prime must have cardinality 3. Okay, but here's the important observation. From the definition, it's all those elements which when you conjugate with H prime, they give you back H prime. This certainly contains H prime, at least H prime certainly is inside this, right? Because if I take G to be an element of H prime and I conjugate by that element G, of course the answer will lie again in H prime, right? If G itself is in H prime, G H prime G inverse is also in H prime. So the normalizer of a subgroup certainly contains the subgroup itself. Now the subgroup of course has cardinality 3 as well, okay. So what does this say? We have just concluded that the stabilizer of H prime has cardinality 3, but on the other hand the stabilizer contains the original subgroup H prime whose cardinality is also 3, okay. So what's the conclusion? It just means this can only happen if the stabilizer is H prime itself, okay. So for any 3 Sylow subgroup, we also conclude the following fact, that its normalizer is itself, okay, or the stabilizer for the conjugation action. Okay, so what does that give us? It helps us determine the kernel. So why did I get here? Because I was trying to say I can try and determine the kernel of this map, right? So I need to find this out. That's the intersection of all the stabilizers. Now I know what the stabilizers are. So therefore, conclusion, the kernel of this map phi is nothing but the intersection of all the stabilizers H prime running over all the 4 subgroups, but the stabilizers are themselves H primes, okay. And this, as we know, is just, in fact, if you intersect any 2 of them, it gives you the identity. So of course if you intersect all 4, you get the identity itself, right? That's clear from our picture. So the intersection of these 4 subgroups is only the identity element. Okay, so what does that mean? It says that the kernel is just the identity, which means that phi is injective. So this part is now done, right? So I just concluded here that this of course means that phi is injective. Okay, already we are in good shape. So let's look at the second part of the proposition, which is we need to show that the image of phi is going to be isomorphic to A4, okay. Now this is again an interesting argument, which is that so let's look at the map phi itself. So we look at the order 3 elements of G, okay. So what I have here is a group homomorphism from G to the group S4 or the group of permutations, and I now know that phi is an injective map. So let me look at the order 3 elements of G, right? So somehow I am basing all my intuition on the fact that I know what the order 3 elements are. So there are these 8 elements whose order is 3. Let me look at where they will map under this homomorphism phi, okay. So let's look at the images of these order 3 elements. So recall there are 8 order 3 elements, which are A square, B square, etc. in G. Observe that since phi is injective, their images under phi are also of order 3. Their images under phi, okay, are also well, what are they? They are now order 3 elements of S4 now, right, of S4 or S4, which is the permutations of X, okay. So at least I know that there are, I am trying to understand what the image looks like. I know at least this much, that the image has these 8 order 3 elements, okay. And why is this? Because if an element has some order, see if X, we will call it something else, maybe if I have an element A whose order is D in general, if A power D is identity and I apply a group homomorphism, this tells me that phi of A power D is also identity, but this is phi A whole power D, okay. Now what that means is that the order of phi A divides D in general, but the order of phi A, since phi is injective, it also means that D, if D is the smallest number such that A power D is 1, then D must also be the smallest number such that phi A D is 1, okay. If not, it will imply that phi is not injective. Okay, so an injective map preserves orders. So that's what I wanted to say here. Let me get rid of this. Let me just go on. So the image is under phi. That's what I want to understand. There are 8 elements of order 3. Okay, now let's look at the symmetric group S4 itself and ask what are the elements of order 3 in S4? What do they look like? Okay, and question, what do the elements of order 3 in what are the elements of order 3 in the group S4? Okay, and the answer is lies in trying to understand the various cycle types. So let's recall what are the various possible cycle types of elements of S4. So these are cycle types in S4. You can have, say, the element the identity element whose cycle type is 1, 2, 3, 4, or I can have a 2 cycle and 2 1 cycles. I can have 2 2 cycles, or I can have an element which is a 3 cycle with a 1 cycle or a 4 cycle. So these are the 5 possible cycle types, and in each case it's very easy to see what the order of an element is of that cycle type. So let's tabulate the orders. So if an element is identity, of course it has order 1. So this is order 1. This is a transposition. So I mean, if I square this element, I will get identity. This again, it's a product of 2 transpositions if I mean which commute with each other. Here again, if I square this element, I get the identity. Now in this case, here is a 3 cycle. So if I cube this element, I get the identity. So the order is 3, and this element has order 4. Okay. So here's the interesting bit, that there is actually exactly one possible way in which you can get an element of order 3, one possible cycle type which will give you order 3, and that cycle type is 3 cycle with 1 cycle. Okay. So what we conclude therefore is that these 8 elements that we know which lie in the image of phi, these 8 elements must have this as their cycle structure. Okay, it's got to be 1, 2, 3 with a 3 cycle. But the proof more or less is done. Now the key point is that elements of this cycle structure must all be even permutations, okay, are necessarily even permutations. That's what we're going to claim. So observe now that the 8 elements of order 3 in the image must have cycle type like this 1, 2, 3, 4. Okay. So in other words, have the cycle type, meaning they should all look like, so every one of these 8 elements therefore looks like some 3 cycle I, J, K, L, let's say, okay, where I, J, K, L are some 1, 2, 3, 4 in some order. So this is what any one of these 8 elements, every one of them has this form. Okay. Now the key point is, suppose I take an element of this form, this can be written as the product of the following transpositions. So I can write this as, let me get the order right. So this is Ij into Jk. So this is the product of the transpositions Ij and Jk. And L of course is not a transposition, so it's a fixed point. So observe, when I write sigma as a product of transpositions, I get exactly 2 transpositions. There's Ij and Jk. Okay, and so which means that sigma is an even permutation. An even permutation. In other words, it belongs to A4. Therefore, sigma belongs to A4. Okay, now what does that tell us? So it tells us that if I look at the image of phi, image of this homomorphism, it was an injective homomorphism, and I want to prove that the image is exactly A4, but at least I know this, that there are 8 elements inside this image. The image of phi intersection A4, at least these 8 elements are certainly in A4. Okay. Now again, it's a simple counting argument. It's all left. So this guy, observe, is however a subgroup. This is the image of a homomorphism is a subgroup. So this is therefore an intersection of two subgroups of S4. So this is a subgroup of A4 if you wish. This is a subgroup of A4. It's a subgroup whose cardinalities are at least 8. Now observe, A4 has cardinality 12. Okay, which means that this subgroup should have cardinality which divides 12. Okay, this is a subgroup of A4 which implies has cardinality which divides 12, which means it's 1, 2, 3, 4, 6 or 12. These are the only possibilities. Has cardinality belonging to this set. Okay, but we know it's at least 8 because of this previous argument, which means that all the other possibilities don't exist. None of these is possible. The cardinality has to be actually 12. This means that image phi intersection A4 has to have cardinality 12. In other words, it's equal to A4. Image phi intersect A4 equals A4. Okay, that means that the image contains A4, but the size, so recall however that the cardinality of the image of phi is the same as the cardinality of the original group G. Okay, because what was this phi? Phi was an injective map from G to S4 to the set of permutations of X, right? So phi was an injective map. So if G has cardinality 12, then of course the image of G under phi also has cardinality 12. So this guy actually has exactly cardinality 12. Okay, so it has cardinality 12, and on the other hand the image contains the group A4 whose cardinality is also 12, which means that these are actually equal to each other. So the image of phi is in fact equal to A4. Okay, so if you identify the permutations with S4 in any which way, what we have shown is that the image is exactly the subgroup A4. Okay, so that completes the thing that we set out to prove, that either H is normal, or if not, the group itself is isomorphic to the group A4. Okay, so along the way we have had occasion to use many different facts that we have learned until now about groups and actions and homomorphisms and so on. Okay.